Okay. So shall we begin? Hello, everyone. Assalamu alaikum. Good morning, everyone. My name is Khalil Raza, and I am the program manager at the ECO Science Foundation. And I'm honored to, uh, uh, you know, welcome you to this webinar on behalf of ECO Science Foundation. And we have been collaborating with the Union of Iranian Societies of Mathematical Sciences, UIMS, for the last year. And we have been organizing webinars with an intent to promote uh, the popularization of science and math in particular among the young scholars and researchers within the region. So this is our 8th lecture in series on popularizing maths and science. And for those of you who are not familiar with the ECO Science Foundation, ECO Science Foundation is an intergovernmental agency of 10 member countries that includes Afghanistan, Azerbaijan, Iran, Kazakhstan, Kyrgyz Republic, Pakistan, Tajikistan, Turkey, Turkmenistan, and Uzbekistan. So our role is mandated to promote regional cooperation in science, technology, and innovation. And of course, that science popularization is one of the key areas that ECO Science Foundation strives to promote. One of the thrust areas. So a quick announcement before we formally begin. So the session is expected to last over an hour, and for the next 45 to 50 minutes, our esteemed speaker will have this opportunity to present his lecture. And if you have any questions, please put it in the chat box, and we'll take them at the end during the Q&A session that we expect to host about 10 minutes. And please keep your mics muted. And if there's any query or comments, you feel free to put it in the chat box. So today we are privileged to have Mr. Imran Parvez Khan. He has joined us as our esteemed speaker. A bit of an introduction about Mr. Khan. Mr. Khan is currently a visiting faculty at Fatma Jinnah Women University at Rawalpindi, and he has a diverse teaching experience and has supervised undergraduate research projects on teaching of topology and recreational mathematics. His research area is topological string theory. He's a co-author of Topology for Beginners that was published by Oxford University Press 2022. And he has earned his MS, Master of Sciences in Mathematical Physics from Comstate University, Islamabad. And his title of his talk is Symmetry of Frieze Patterns. So, and over to you, Mr. Khan.
Thank you very much, Mr. Khalil. And I'm grateful to ECO SF for giving me this opportunity to talk at a very important webinar series because promotion of mathematics is much needed in this region. So my congratulations to you also for holding such a wonderful webinar series. So the title of my talk is Symmetry of Frieze Patterns. So there are two terms. So I would like to begin with the explanation of these two terms. But before that, I would just briefly like to wish Ramadan Mubarak to all those who are celebrating. And I would also, when I was told that the day of and the time of my talk has been scheduled to 14th March, so I did not resist to change it uh, because of the following reason that today happens to be what is called Pi Day. And the reason of calling it Pi Day, in fact, it's not the pie that we eat, but the value of mathematical constant pi is 3.14. I'm sure many of you must have studied about it in your school. So, according to certain date styles, this number is interpreted as 14th of March. So, UNESCO in 2020, in collaboration with International Union of Mathematics, declared this day as the International Day of Mathematics. So you should be very happy that you are celebrating the International Day of Mathematics in a way by attending this talk on a mathematical subject. So you can see their website for further details about this day. So this day is now celebrated every year all over the world, including Pakistan. So let me first talk about what is symmetry. So we have a general idea about symmetry, like we see it in flowers, in nature, in leaves. As I've shown some pictures, the wings of a butterfly, the snowflakes, and the leaves. All of these are, God's creations. They are found in nature. They are not man-made. And the nature prefers symmetry, whether it's human body or any other natural object. It's symmetric most of the time. And copying the nature, man-made objects also have symmetry, like man-made aeroplanes. When man invented aeroplanes, so there are two wings to have the balance. So this idea of balance and symmetry is very important in nature. So yes, not only for the purposes of beauty, though in my talk I'll be focusing on the beauty aspect of it, but also because of the functional aspect of it. The things won't work properly if they're not symmetric. So let me begin with the definition of symmetry. Any harmonious or aesthetically pleasing proportionality and balance is termed as symmetry or symmetric. Now, the other term I use is frieze pattern. So, what is a frieze pattern? This again is a simple idea. It's an infinite strip with a repeating pattern. And such patterns are called either frieze patterns or border patterns. So, having the basic understanding of what is symmetry and what is frieze pattern. So, that. Let's see some examples of frieze patterns. So here below are some examples. So mostly the frieze patterns are found on walls in our homes. We find it in the crockery we use, the cups and plates, and also uh, in our houses. In we place curtains and we use, bed sheets, and so there are some patterns. And that is the idea, that it's a repeating pattern. It begins and there's some object that we choose to be the primary object, and then it is repeated and a pattern generates. So these are decorative patterns. So let me begin with now the basic mathematical idea behind it. So how mathematicians look at frieze patterns and their symmetry. So they define certain symmetry operations. The way in mathematics we have, some operations, like in arithmetic we have addition and subtraction and multiplication, division. So similarly in symmetry we have certain operations. So here there are some operations, and I apply it to my photograph just to uh, emphasize that in order to generate a frieze pattern, you can start with any object, even if it's, your photograph. Any object, that object has no condition on it, but after applying the symmetry operations, we'll see that how a pattern generates. So the first symmetry operation is translation. So in mathematics, when we move an object forward, so that is called translation, that we have translated the object. So my picture was, initially there, and I moved it a little forward, and then by repeating this process, I'll generate a border pattern. Not a very interesting one, but it will be a frieze pattern. The other operation that I can do is called glide reflection, and it is a combination of two patterns. So let me show, and it will become easy to see that now I not only translate it, but after translating, I also do what is called a horizontal flip. So I have, we call it horizontal flip because the imaginary line that I place on the object is a horizontal line. So I flip my object around that line. So translation plus horizontal flip is called glide reflection. And continuing on this operation will generate a Frieze pattern. A little more interesting than the previous one. Then the third operation is rotation by 180 degrees. And the effect is similar to glide reflection, but nonetheless, it is a different operation. Then there are two more operations. One is called vertical mirror. So what this does is, as you can expect, that I place a mirror vertically to my object, and it reflects the left to the right. In the original photograph, I'm looking at the left, but after applying the vertical mirror, I'm looking to the right. So continuing on again, we can obtain a Frieze pattern. And then horizontal mirror is similar to the glide reflection. Uh, so it's just a matter of where you choose to the uh, place the object after applying the horizontal mirror. So if I place it right there with the original, then the pattern will contain uh, upside down images of myself counting on after applying translation. So translation is always there in a Frieze pattern. Every Frieze pattern will have translation, but rest of the operations, that depends, and that is the purpose of this talk, that we'll see that which patterns contain whether the horizontal mirror or the vertical mirror or the glide reflection or the rotation or all. So we'll talk about these operations in the coming slides. Before that, I would just like to introduce a bit of the notation. And it's not hard to understand the notation, so that's why I want that, those who are attending this talk and taking time out to attend this talk, they must, after this talk, be able to not only recognize these patterns around when they see, but also be able to classify them according to their notation. So there are four characters in the notation. As you can see, that there's a letter P and then three numbers. So of these four characters, the first one is always P, and the significance of that P is not important uh, for our purposes. And the last one is always a number. The second and third one correspond to the vertical and horizontal axes respectively. One indicates that there is no symmetry corresponding to that position. And then I have mentioned what. So the vertical and horizontal axes are more important. M at a vertical or horizontal axis means that there is a vertical or horizontal mirror in that axis. And if there is an A in these two positions, then it means that there is a glide reflection in that axis. So let me elaborate it further. So the last number tells me whether there is a rotation or not. And the rotation is only by 180 degrees if it is. The third number shows me whether a horizontal mirror or glide reflection is present or not. And the second number tells me whether a vertical mirror is present or not. So P, like I said, it's just a convention. It is called primitive cell, and we do not need to go into that detail. So the last number is denotes the rotational symmetry, and it is 180 degrees always for Frieze patterns. So the importance of this topic is that all of the Frieze patterns, you imagine all of the Frieze patterns in the world, can only be understood by just 7 combinations. There are only, all the patterns can be reduced to 7 basic types of patterns. So that is my main objective, to explain that you take up any pattern in the world, and it will be either of the 7 patterns that I'll discuss in this talk. So just to make it very simple, so I've started with a remember that recall that our first operation is translation. The simplest operation is translation. So I can begin with any object. So here I have started with the slant line, and I have repeated the slant line 5 times, and I can generate an infinite strip from this slant line. So that is, one way of doing it. Then I can use some of the mirrors. So here I have the same 5 lines, but now I apply the horizontal mirror, and you can see that horizontal mirror in the red. So a new pattern has generated. So the difference between the previous pattern and this one is that the previous pattern has no horizontal symmetry. If you reflect the pattern, then the pattern would change. These are backslashes in the first pattern, and if you reflect it, they will become forward slashes. So it has no symmetry other than the fact that it's being translated. But the second pattern has more symmetry in the sense that if you reflect the pattern, so these are kind of forward arrows, and if you reflect the pattern, it wouldn't change. So one way of defining symmetry is that the object remains unchanged. If you have a ball, so whether you rotate the ball this way or that way, it remains a ball because it's a very highly symmetric object. So meanwhile, side by side, I also want to help you understand the notation, that the first pattern is called P111 because it has no vertical mirror, no horizontal mirror, no rotation, 180 degrees rotation. But the other pattern has an M in the second, M in the third place, which means that it is a horizontal mirror, as we have just discussed. Then the third pattern, I use the same slant lines. Now, what I do is that I reflect them, but I just do not reflect them. I reflect them after translating. So red arrow shows that I first translated the slant line and then reflected it. And as you recall, this operation is called glide reflection. And in the notation also, we see that there is an A present in the third position, which means that there is a glide reflection in the horizontal axis. So for the fourth pattern, I have again the same slant lines, but this time there is I've reflected them along a vertical and imaginary vertical line. And in the notation also, we can see that now M is placed. Notice the difference between second and fourth pattern, that in second pattern, the M is at the third place, and in the fourth pattern, the M is at the second place because that is how the notation is defined, that this M shows that there's a vertical mirror as opposed to a horizontal mirror. And you can see the imaginary mirror emphasized by the red line. So we started with the slant line, but we kept applying the vertical mirror, and the pattern generates. The important thing is that a pattern generates this way. And the fifth pattern here shows that again the same slant lines, but now I have an M in the second place, which means there's a vertical mirror. But there's also an A. So that means that whatever pattern I have in the initial place, I translate it and then I also glide it. So there are two bars which form a V shape, and then I translate them and then I reflect them, and they become, if we say that there's a V shape and then we have an inverted V shape, again the point is that there's a pattern generates. And when you create a pattern this way, it has the advantage that now we also have a rotation which is emphasized by the red dot here, that if you, so rotation has a center, rotation always have a center. If you open the door knob of your door, so that there's a center around which the door knob revolves. So rotation always have a center. So here the center is emphasized by the red ellipse, and which means that if you rotate the upper V by 180 degrees, the pattern wouldn't change. That is what is meant by symmetry. If you rotate the pattern by 180 degrees, you still get the same pattern. So it is symmetric. It is more symmetric. The pattern shown below, before, the patterns that are in front of you above the last pattern, they don't have rotational symmetry. If you rotate any of these patterns, they would change their shape. But this fifth one, even after being rotated by 180 degrees, would retain its shape. So moving on to the sixth pattern. Now this one is called P112. Why? Because I started with the same 5 lines, but what I now did, I neither applied a vertical mirror nor a horizontal mirror, but what I did, I rotated that line by 180 degrees, rotated the line by 180 degrees, and a new pattern emerged. And the notation also shows me that there's a 2 at the last position, which means that there's a rotation by 360 by 2 degrees, which is equal to 180. And the seventh pattern is, as you can see in the notation, it has got everything. It has got both mirrors, the rotation, and we'll see that automatically it will also have glide reflection too. So I apply the vertical mirrors, and then I apply the horizontal mirror. So notice that first I apply the vertical mirrors. So it's the pattern without any symmetry. I apply the mirrors, vertical mirrors. Then I apply the horizontal mirror. So V turns into a cross sign. So initially I had V, then it became a cross because of the horizontal mirror. And after having both mirrors, it automatically has rotation symmetry also. So it has got both mirrors and rotation symmetry also. And if you glide any of the crosses and translate it, so it will you know generate the same pattern. So this one has the highest of symmetry. And later on I'll also show real examples that are found in the world. So let me quickly go through this another example also. So again, there are some arrows type thing, and you can keep translating them to generate a pattern. And now in the second line, now I think you would be comfortable to see, you know judge yourself that what has been done, what is the difference in the first line and the second line. So there's a horizontal mirror applied, and the pattern is created. And again, I'm pretty confident that in the third pattern also you can yourself tell that what we have done, we have applied the horizontal mirror, but after translating a bit, which is uh, glide reflection. So it's not the simple reflection, it's the glide reflection. So again, you can see the notation also. And so in the third pattern, we first translate and then reflect, so which is the glide reflection. And in the fourth one, we have the pattern, original pattern, but after we apply the vertical mirror, we obtain a new pattern. And in the fifth one, we apply the vertical mirror, but then we also apply glide reflection, and still another new pattern is generated, which has rotational symmetry also. In the sixth pattern, there's only one symmetry, which is the rotational symmetry. It has no, if you apply the vertical mirror, the shape would change, the pattern would change. If you apply horizontal mirror, the pattern would change. Down arrows would become up arrows, and up arrows would become down arrows. It only has the rotational symmetry, which will preserve the pattern. And then the highly symmetric PMM2, which again, makes it, you can look at it as some X shape, or if you look at it like brackets, angle brackets. So there are both ways to look at it because it's a pattern. So the claim is that these are the 7 patterns. All of the Frieze patterns would belong to either of these 7 patterns. So it has, you can see the vertical mirror and horizontal mirror. So I would like to skip this one. And so the idea is that you can begin with any object. Here it's a flower, and you can keep translating the flower to generate a pattern. But then, of course, you can apply symmetry operations to come up with more beautiful patterns. You see, the third pattern, we see it in, in objects around the world, man-made and both nature's creations. So you see in the fourth pattern, there's a flower, with a petal on the right, but then on the left, then on the right, then on the left, because of the application of the vertical mirror. So you can create all sorts of beautiful patterns with these symmetry operations. So all these patterns have, very minute differences, uh, but with the help of these symmetry operations, we can understand those minute differences. So now comes the interesting part, and I would encourage you to, uh, think about it. So I haven't given away the answer right away. So it's a pattern found on some wall. So we can also find it, in like Muslim world is full of such patterns and uh, such arts and such patterns. Uh, so now I would like you to think a bit that, of course, this pattern has a translation symmetry because there's a blue object, a blue octagon, and it keeps translating at the pattern generates. But now we have to ask some other questions, whether this pattern has horizontal mirror or not, and whether it has vertical mirror or not, and glide reflection, and what about the rotation. So it's a bit tricky here, because notice that the blue octagon on the left, it passes over the brown octagon, but on the right, it passes underneath the brown octagon. So here's the trick. Now, if you apply the vertical mirror, then uh, the the blue octagon on the left, the original, we have to preserve the original pattern, so the blue octagon passes above the brown one on left. But if we apply the vertical mirror, then the blue octagon on the right will pass above the brown octagon, and the pattern would change. So we don't want that. So that's why I would say that this pattern has no uh, vertical mirror, because by applying the vertical mirror, you change the over and underneath thing. Same with the horizontal mirror, that if you apply if you horizontally flip the blue octagon, then uh, it was supposed to pass above the brown octagon, but when it comes down, it has to pass below the brown octagon, but that won't happen. So if you think that, but there's one symmetry that it still has. If you rotate the blue octagon by 180 degrees, then that would happen. because you see that the blue octagon passes uh, on the top left, it passes over the brown octagon, and in the bottom right, it also passes over the brown octagon. And now, if you rotate by 180 degrees, that pattern is preserved, that style is preserved. So, yes, we would say that this pattern has P112 symmetry. That is, it has no vertical mirror, no horizontal mirror, but yes, we can rotate it about the center shown in the red. Then there's this another pattern, and so I would like to give you a moment to think about it. What symmetry it has? Again, of course, it has translation symmetry. There's an object, a brown one or the gray one, and that keeps translating. And the spaces also create the pattern. So it's a beautiful pattern. Uh, and I think it's very clear that it has a horizontal symmetry, right? It has a horizontal mirror. And that is also clear that it doesn't have a vertical mirror. And you see, these symmetry operations are important. Now, I hope these examples are more clear to see that if I reflect the whole pattern upside down, the pattern wouldn't change. You cannot tell whether somebody has flipped it or not because of the symmetry. So that is the idea of symmetry, that things preserve their shapes even after an operation. If I flip it, nobody would notice that I have flipped it because the pattern is symmetric. But if I, vertically flip it, then uh, it's very noticeable because it's pointing to the right, but then it would point to the left. So yes, this has a very simple vertical mirror symmetry, P1M1. Then this again is a beautiful pattern, and I think a common one, and but we won't have looked at it through the eyes of a mathematician. So again, it has a translation symmetry. This is a leaf kind of thing, which is being translated. But what about? So yes, again, it has apparently it doesn't have a horizontal uh, mirror because because of the absence of the leaf, where the leaf is underneath the curve. If I apply the horizontal mirror, it would become upwards, where while it is not there actually. So it has no horizontal mirror, but I understand that you can see that there's some kind of horizontal mirror. So that is called glide reflection, that you can do the horizontal flip but after translating. So once you translate, then reflect. So yes, that symmetry is there. And of course, there's no vertical symmetry, no vertical mirror, because the pattern is sort of moving to the right. And if I apply the vertical mirror, it would go opposite way. And the same would happen if I try to rotate the pattern by 180 degrees. So the pattern would change completely. That is something we do not want. We want it to preserve its shape and the pattern. And so yes, it has got glide reflection and P1A1, simple P1A1. Then this pattern is also interesting and beautiful, uh, because and that is something I would like to say, that if you find it beautiful, then there's a reason behind beauty. Usually we do not talk in those terms, that there's no reason, but that's what we are trying to do when we study symmetry mathematically, that there is a reason behind beauty. One of the reason is, like, most of the buildings we build, like yesterday I was looking at the mosque that is in my locality, and it's a very symmetric mosque. So yes, in Muslim architecture, we usually try to build things in symmetry and proportion. The Nobel Prize laureate of Pakistan, Professor Abdus Salam, who won the Nobel Prize in physics in, I guess, 1979, if I'm not wrong. So his work was on mathematical symmetry applied to physics, but he said that he was inspired by the symmetry of Badshahi Mosque. Badshahi Mosque is a very famous mosque in Lahore, Pakistan. So he said it the symmetry of its minarets and the symmetry of the mosque overall, it inspired him to see a mathematical symmetry in it. Of course, there goes a lot of detail into that. It's not just that, but yes. So symmetry is one of the reasons we find things beautiful is symmetry. But why I'm taking a lot of time on this, because it's a very beautiful pattern, and the reason is that it's highly symmetric. So you take up an object, any of the objects that you see in this pattern, and you can translate it to generate the pattern by repetition. But then it also has rotation, as shown by this red uh, ellipse. So there are, I'm showing you the rotation centers, the points where if you rotate the whole pattern around these points, the pattern wouldn't change. You cannot tell whether one has rotated or not, because the pattern would remain the same. Then there's horizontal mirror, very clear horizontal mirror, very clear vertical mirror. So as you expect that this is our most grand pattern, the seventh one, which has got everything. It has got vertical mirror, horizontal mirror, rotation, and automatically the glide reflection too. So yes, this is the PMM2. So I guess this one is the last pattern that I would like to talk about. So this is again a common pattern. I think it's a common pattern found in both architecture on walls and in in clothes. But let's see it in terms of symmetry operations. Of course, it has got a translation. Uh, but if we try to find any vertical mirror, so yes, it does has a vertical mirror because it's a T kind of shape, and that T shape, if I you know apply a vertical mirror, so that the pattern is preserved. So yes, it has a vertical mirror. But if I apply the horizontal mirror, then the T becomes inverted T, and that's not in the original image. So it has no horizontal mirror. And again, those who think that there is a kind of horizontal mirror, so they are correct. There is a horizontal reflection if you translate, and which is called the glide reflection. So yes, if we reflect but also translate a bit, then the inverted T matches with the inverted T present already in the pattern. The difficult thing in this pattern is to recognize the rotational symmetry. As I said in the previous for the previous pattern, that rotation occurs at a center. So you open the door knob, so there's a center about which you rotate. So you cannot just rotate the full pattern. There's a particular point where you have to rotate. So let me show you that point. So yes, there's vertical mirror. So this red ellipse shows the rotation point. That is the only point where we can rotate this object such that the whole pattern does not change. If I rotate around this red dot, the so that is a symmetry of this pattern because the pattern remains unchanged. You won't notice that, and it would smoothly merge. The upper side will merge with the upper side, and the lower side will merge with the lower side. So yes, it has a rotational symmetry, and but a bit tricky to recognize that. So I would encourage you to look around and I hope it automatically happens that after listening to this talk, you will be able to see the patterns. Like for me also, like there's a window in my house, and I started looking at it. Okay, it has this and this type of pattern, and I tried to apply rules. Okay, whether it has vertical mirror or not, or horizontal mirror or not. So, so I think it's a very easy topic, and it helps you see the world in a more fun and interesting way. You start to look for patterns in the buildings around you, and in the blankets and in everything. There are such patterns. So I think this is my last slide. So I'll end here. So I've just shown another rotation point of this pattern. So yes, they are very selective rotation points. So okay. Yes, the name of this pattern. Since it has a vertical mirror and no horizontal mirror, so this is the PMA2. So in conclusion, that's I would say that these are the 7 Frieze patterns. No matter which pattern you come up with, you find in the world. I've heard that in Spain, Alhambra, there are a lot of such patrons. And the Muslims of those days did know the mathematics behind it. In fact, there was a Dutch artist called Escher, Escher, very famous. And he visited Alhambra, and then his style of paintings changed absolutely. And his paintings have this a lot of symmetry principles behind those, and many mathematicians study it because that's what Escher did. He used these classifications, and of course a bit higher than those also, to incorporate in his artwork. But the 7 patterns, and they are more than enough. Now I would encourage you, and I would be very happy if you are able to classify the things around you according to these 7 patterns. Okay, so this one's left, so we have got some time. So I'll also like to discuss this one. Again, this is very beautiful, and this is also tricky. Recall that the first pattern in this series, this one has that tricky part. As you can see that there's a strip that goes above, so the border of the blue object passes above the border of the brown object. So it has that thing which, because of which we would violate the symmetry if we try to apply the vertical mirror. Because if we apply the vertical mirror, the same thing would happen, that on the left, the border of the blue pattern passes underneath, but on the right, the border of the blue pattern passes over the browns one. So if we apply the vertical mirror, so that would violate the pattern style. So we cannot have a vertical mirror, and clearly we cannot have horizontal mirror. The pattern above is the top is totally different from the bottom, so we cannot have a horizontal mirror either. No glide reflection, no rotation. So despite its apparent symmetry, it lacks symmetry in mathematical terms, and that's why this pattern is called P111. That is, it has only one symmetry, and that is translation. So, in the end, I would just like to give you an what is called algorithm for deciding. So, it's not just haphazard way of thinking about patterns, and there's no mystery about it. So these are 7 groups, and you can use this algorithm to understand and to decipher and to reach to the uh, right pattern, right notation for the right pattern. So you begin with the question at the top: is vertical reflection present? So if So if the vertical reflection is present, so imagine if the answer to that is yes, then I ask the second question, is horizontal reflection present? Well, if both reflections are present, by reflection I mean mirror. If vertical mirror is present and horizontal mirror is present, then simply the answer is PMM2. The pattern is PMM2. But if vertical is present and horizontal mirror is not present, then I have to ask again another question, that is uh, twofold rotation present or not? By twofold rotation, I mean that 180-degree rotation. So if that is present, then the group of frieze pattern is PMA2. The type of frieze pattern is PMA2 because it has a vertical mirror and a glide reflection. But if it has the vertical reflection, vertical mirror, but no glide reflection, then it is simply PM11. Now, the second side, if vertical mirror is not present, then I ask if the glide reflection is present. And if glide reflection is also present, then I ask if the horizontal mirror is present. If the horizontal mirror is also present, then the pattern is PM, P1M1. But if there is glide reflection but no horizontal reflection, so there is glide but not horizontal mirror, as we saw in some of the patterns above, then it is the type of frieze pattern is P1A1. And if the horizontal glide is also not present and the vertical glide is also not present, but there is twofold rotation, then it is P112, that there are no mirrors, but there's rotation. And lastly, if there is no vertical reflection, no glide reflection, and no twofold rotation present, then this group only has translation, and this is P111. So here I end my presentation. I'm grateful to everyone, and once again, I congratulate ECOSF for this initiative. And I recently had a chance to visit one of the member countries of ECOSF, Uzbekistan. And I think there is a lot that we should do for promotion of mathematics in this region. So here is my email address. I welcome all the participants to provide me their feedback and ask me any questions they would like related to mathematics or my talk. And I also expect that with ECOSF and Dr. Manzoor Sumro, that I would love to contribute to this goal of mathematics promotion in this region with them in future also. Thank you.
Thank you, Mr. Imran Parvez Khan, for this very interesting presentation and the lecture. Well, I've got a few questions on the race pattern. So this was the first opportunity that I had looked at the patterns in a way that you have provided the framework. So as a layman, we just look at the patterns, but we do not recognize the framework that you have just presented. Um, can you go back to one of your first few slides where you have shown or demonstrated some of the natural symmetrical objects or the
Yes, I think that was the very first one, I guess.
yeah.
These ones?
Um, so I understand that most of the patterns that I see here, uh, is this the orange one is a jellyfish?
Yes, it is some kind of fish, what we call the starfish usually.
So these patterns are quite predominant in the living species. For
True.
instance, you see there's a plant, there's a butterfly, there's a
Yes, yes,
bee.
true.
Yeah. So we don't see much of those freeze patterns in the nature in the non-living species. For
Uh,
instance, do you see freeze patterns in the mountains or seashores or the earth's crust?
yes, you're right. You're absolutely right. Uh, Actually, so these are the freeze patterns. So these are called one-dimensional patterns. Uh, but then, you also have more complicated symmetry patterns, which are, two-dimensional ones. So, but you have asked a very interesting question, and I would try to answer that. For example, there's tree. Apparently, a tree hasn't got much of symmetry, but the symmetry that tree has is called what is called the fractal symmetry. And let me not overwhelm you with a heavy jargon. Fractal is a very basic idea. So you start with an image, so we call it self similar, that there's a branch of a tree, and then on that branch there's another branch of the tree, and on that second branch there's a third branch. So that is how you create a self similar pattern, that you begin with one branch, but then you have on that branch you have another branch, on the other branch you have another third branch, and on the third you have the fourth branch. So as you talk about the mountains, so they have what we say, one, that they have the kind of fractal symmetry. But here I would just like to say that yes, I agree uh, that but if a child would draw a mountain, at least he would draw it in triangles. So that much is there.
Right. And thank you for explaining this. So this was just my observation that whatever we see in the nature, it's mostly most of the time, except the that snowflake, that's a non-living
Yes.
species, right? Apart
Even
from
if,
that,
if you talk about the waves, I would again say that if a child would make a wave, he or she would make it symmetric. Like it's a wave like that, a sea wave. Like, I agree that in reality they are not that symmetric, but sometimes you find a pattern.
I think there's something substantial about the living species that either it's plants, insects, animals. Um, we have that natural tendency in a design that we in the living species that we have this symmetric patterns as we see in the slide here. Um,
True. Now that you say that, makes me think also that yes, there's something special about the living beings and symmetry. Uh, and like I said in the beginning, that if a bird won't have the two wings, it won't be able to fly. You need two wings. So yes, symmetry has a function also. It's not just mere beauty. It has a function also. Like and if a man is fortunate unfortunate and he hasn't got one leg, he has difficulty walking. So symmetry is not just for beauty, but it has function also.
my second question that relates to the first question. So, what we see in the medieval Islamic structure, or even some of the other religions, we see these patterns in the ancient building structures. When was the time when the frieze pattern, the study of frieze pattern, was originated? So I would just want to. So the context of my question is: did the evolution of frieze pattern by a layman to put this thought into design came first, and then as a result of that pattern, there was a origination of this study? Because still today, a lot of um, artists or artifacts that those we see in the market, uh, these architects or the fine artists, they may have contributed to the design, but they may not know the framework of the frieze pattern.
Hmm. Well, the as much history as I know, that the frieze patterns for the sake of arts, for the sake of decoration, are very old. Even like since the in every culture, so they are, I think, more categorized according to the culture. Like in Chinese culture, the Chinese crockery is very famous, and that crockery used to have some border pattern. They prefer to have some border. uh, Similarly, in Islam, that drawing of human face was not allowed, so they were led to making patterns, creating patterns. Now Greek and Roman culture, because they are very old cultures, they are since BCs, before the time of Christ. So those cultures, like, they built a lot of pillars and huge buildings. So those buildings used to have these decorative patterns, as the one shown in this slide. So they used to have pillars and thing, and there was this some sort of frieze pattern. So yes, they are very old, and I agree with you that the artist found these patterns beautiful, and they created those patterns without knowing the underlying mathematical categorization and classification of these patterns. So it's true that the artist made these, but he didn't know whether he's using the horizontal symmetry or the vertical symmetry.
Right. Thank you. And so I'll take a few questions from the audience, and we have
Sure.
a couple of questions or comments in the chat box. So one is uh, the name indicates Sumro's iPhone. I perhaps it is Professor Sumro. Um, so he first has complimented you, and then he has asked that what's the message that you would like to for the participants to take home, especially the layperson in mathematics like me. So that's the
Uh,
question.
Well, thank you, Dr. Sumro, for taking out time to listen to my talk. Well, my message is that be curious, and look around, and find patterns, and not just enjoy their beauty, but also think about those patterns, and think about how those patterns came into being. And let me also say that in a book I was reading that, because I know a bit about Dr. Sumro. So in a book I saw that the patrons of Sindh are also studied a lot, and the Sindh Ajrak. So the patrons on that are also studied by those who study symmetry.
Thank you. And we have one more question from Mr. Payam Siraji. So he mentions that your talk was about the symmetries, which are important in art. Another question is about proportions. What proportions are important or are preferred in art? So I'll repeat. What proportions are important and are preferred in art?
Well, it's a very good question, and I only know of one, and that proportion is called the golden ratio, or the golden proportion. And that is about, it's a number, and that we can derive that number mathematically. But right now, you see, as there are certain numbers that are important in mathematics, as I began with pi, 3.14. So it's an important number in mathematics. So there's another number that is called 1.618. So this number is roughly, it goes on, but it's 1.618. And that is something I would say that it's an important number, and it's an important proportion. And proportion in the sense that they say that the things that are in the ratio of 1.618, they are, again, they are beautiful. And by that I mean I have really applied it, that once I was, I asked a carpenter to make a table, a writing table for me, and I gave him these dimensions. So if I chose the length of the table to be 7 feet, I multiplied 7 by 1.618, and then the other side was 7 times 1.618. So that is the idea. Like in history, they used to, if they make the window, so how to choose the length and width of the window so that it's beautiful. It's not, nobody would like a very wide window or a very narrow window. So we want it to be, some balance and proportion. So yes, that is also a very interesting subject, and that's called the golden number. It's so important in history for these reasons. Like, not only that it's in mathematics, it's important in mathematics, but that is the ratio. Your usual A4 paper, that is also designed according to the golden ratio, that how to choose the width of the paper and how to choose the height of the paper. So, these are very these are not just, randomly designed things. There are reasons behind those. So yes, that's what I would say, that the golden ratio is important, and the golden proportion 1.618 is important in both arts and sciences.
Thank you. I think we'll take one more question, and it's from Professor Sayed Kumail Tebi, President of the ECO Science Foundation. So he would like to know, does any asymmetric issue affect such symmetric patterns?
Let me answer it in that way, that the way symmetry is important, uh, asymmetry is also important. So I would like to give an example of science. Uh, Louis Pasteur, who discovered penicillin and many important things in science in the early days of science, when people used to die of simple flu, common flu. So the molecules and these objects in chemistry, and so they also come in symmetric shapes. They either come in a very precise shape which has a symmetry, whether it's a cube or it's a octagon or it's a tetrahedron. So they are, they come in pattern. So, but there is a molecule which has, say, say it has a say it has some asymmetric object on the left. Now that molecule is very symmetric to its partner molecule, which has some object on its right. So you see, one has the signifying, well, the distinguishing object on the left, the other has a distinguishing object on the right. But now they look very similar, but they are, mirror images of each other. But the point is that asymmetry is important, that one molecule is used uh, to what I should say, used to treat human beings. The other molecule has the effect of a poison. So yes, here asymmetry uh, does affect in the say that in the way that the mirror image of that particle or that molecule, if you use the right molecule, then it will be beneficial for health. But if you use the mirror image of that molecule, then that acts as a poison. So not in arts, asymmetry is not an issue in arts, but asymmetry is an issue in sciences.
Right. Thank you, Mr. Imran, for this great and interesting lecture and presentation. We thoroughly enjoyed, and on behalf of ECO Science Foundation and UISMS, my gratitude to you for taking this time and presenting this to us. So again, I would like to thank everyone who joined us, and we will continue to host the lectures like this, and we'll keep on inviting the scholars and learned speakers as Mr. Imran Parvez Khan. And we look forward to hosting similar webinars in the future as well. So we do this every month, and thank you to Professor Rejali as a partner. Thanks everyone, and that brings to the end of this webinar. Take care.
Welcome. Thank
Good
you
day.
very much. Good day.